Hello, everyone, and thank you for attending today's webinar, Combining EBSD with Serial Sectioning to Investigate Additively Manufactured Microstructures. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all your questions. A copy of today's slide deck is available in the resource list widget, which looks like a green folder. For this webinar, we'll be using the media player to display the slides. You can expand your media player by clicking on the enlarge or full screen icons in the top right corner of the media player window. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier or via the EDAX website. Now I'd like to introduce the presenter for today's webinar, Dr. David Rowenhorst. Dr. Rowenhorst received his PhD in Material Science and Engineering from Northwestern University in 2004. His doctoral work used 3D microstructural characterization to analyze particle coarsening, or Ostwald ripening, in lead and tin systems in microgravity environments. Dr. Rowenhorst joined the U.S. Naval Research Laboratory, or NRL, as an NRC postdoctoral associateship, and in 2006 continued on at NRL as a staff scientist in the phase transformations and joining section. His work continues to concentrate on advanced characterization and analysis of microstructures, especially within an integrated computational materials engineering, or ICME framework, including 3D characterization of grain growth in polycrystalline materials, phase transformations in high-strength steels, and the 3D microstructures associated with additive manufacturing. Now over to David.
Great. I appreciate the introduction. I'm going to assume that you can hear me just fine. All right. Good. All right. So, yeah, I really appreciate the chance to present at the seminar today and talk about this 3D analysis. So we're going to be talking about looking at how do we look at materials in 3D? Why do we use EBSD? And why is that so important for looking at these additive microstructures that we're seeing? So pretty much concentrating on one data set today. It's going to be additively manufactured 316L, but it's quite a dense data set, so there's actually quite a bit of information. But before I start, I just want to give everybody a chance to, if you don't know where NRL is, the U.S. Naval Research Laboratory, I want to give you a little bit of orientation on that. So we are actually located in Washington, D.C., and so here you can see a lovely map. And while all of the interesting things are all up here in this part of the map, and I do apologize, there's about a couple second delay between what you're seeing and what I'm moving, but we're located down here in this blue star, so we're kind of down in the south part of Washington, D.C. We were founded in 1923, and this is what NRL looked like back then. I really like this picture because the thing that's kind of fun is that my office still sits in that window. And so I actually get to work in about a 100-year-old building. It was the original foundry for the lab, but now it's where our characterization is located. A lot of still our physical metallurgy is located in that building. But we've certainly expanded since then. This is what it looks like today. We have 2,500 scientists in 4 different divisions looking at things like space sciences, ocean and atmospheric sciences, systems, which include things like optical systems, radars, those types of things, and materials and chemistry. Some of the biggest developments we've had in our history is the early developments of U.S. radar. The beginnings of GPS started at NRL. First people who said that we should start launching atomic clocks into space and use that for tracking position were at the Naval Research Lab. And actually the foundations of fracture mechanics were really started here at NRL as well. So that's just a bit of our history. And if we ever get to fly again, and you're getting to fly into Washington, D.C. at Reagan National Airport, you might see this building as you fly, and this is our headquarters there. And so if you're flying in, feel free to wave and say hello. But this is what our outline for the talk is for today. We're going to be looking at 3D serial sectioning, and really this idea of moving from qualitative to quantitative. Why do we use 3D serial sectioning? And then why EBSD is so important for this. We'll go over a brief overview of the reconstruction methods. And I'm also going to have a brief discussion of the NLPAR algorithm and how important that was for the work that we're looking at today. And then finally, looking at some analysis. What kind of data can we extract from this type of these type of reconstructions? So there are all sorts of different 3D techniques that one can use for the analysis materials, and they really span a lot of length scales. We have, at the very smallest length scale, we have atom probe, where you're looking at actually the position of individual atoms and how they're arranged. Very good for extracting nanoscale composition variations, those types of things. If you want to look at nanoprecipitates, there's electron tomography down to the TEM. There's fib serial sectioning, if you're moving up length scales, where you can look at things that are around on the micron level. And then as you move up, there's also the femtoscale, or the femtosecond laser machining now that was really pioneered by Teresa Pollock at UCSB. And that's another milling technique that occurs. And then at the larger scales, you have things like microtomography and mechanical serial sectioning. And what I've plotted here is kind of a rough estimate of your resolution versus your field of view. And this line that runs through it is kind of this magic line of you need to have a resolution of 10 voxels per item. So it really doesn't make sense to have anything that exists within this domain. You're talking about just not having enough voxels within your field of view in order to resolve anything useful. But the other point I want to have here is what we're really looking for, if you want to look at statistical microstructures, are these very large left-hand edges. What that indicates is you can collect a very large volume while still maintaining a very high resolution. And so that's where we see that mechanical serial sectioning really has an advantage over a lot of these techniques, is that it has a very large ratio there. And so if you're looking at something you want to collect that is on the scale that you need something like a micron of resolution to resolve, but you need to collect thousands of them, mechanical serial sectioning is really the best way to go. Now, the procedure for mechanical serial sectioning is not complicated, right? This is something that's pretty easy to grasp. What we're doing is we're simply, usually in our case, polishing. So we're using just standard polishing techniques to remove anywhere from about a half micron all the way up to over tens of microns of material. For the most part, you're looking in that smaller range, though, where you're going to be looking at about 1 micron of removal rate. We do this with this standard polishing methods. Acquire a digital image. This is not really a difficult thing to do. Repeat that at least 100 times, if not more. That's getting a little bit more difficult. That's one of the things that does kind of make things, you realize, oh yeah, I can certainly collect one good EBSD map. Now can I do the same thing hundreds of times over and over and over again without messing up? And then when things get even more difficult is aligning all those sections, making sure that they're all stacked together and aligned properly. And we'll talk a little bit about how we deal with that in our particular cases. And then the final thing, and the most difficult thing, and the thing that people don't often appreciate, is that the most difficult thing to do in all of this is to segment the structure. How do you clearly differentiate what is an important feature within your structure? And this is where things get very, very difficult. So I'm going to give you an example. And here is 2 micrographs. On the left is beta 21S, where we've actually decorated all the grain boundaries with alpha, and we've been able to etch that using a chemical etch. And you can see that we can fairly clearly identify nearly all the boundaries. Notice we don't get all of them, but this is an exceptional case. This is exceedingly unusual. On the right, we have an etch sample of 316 that's been processed with additive manufacturing. And there, if I ask somebody to build an algorithm to extract all of the grain boundaries, they would have a very difficult time. The brightness and contrast is all over the place. You see all sorts of different features. You may say, well, I can I can build a machine learning program that can do that, but then you need to make sure that there's a training data set for you to start doing that. And you'll find out that it is really just as difficult to do some of the machine learning things as it would be to kind of custom make your own segmentation program. And this is why we don't often use optical microscopy for serial sectioning, is because when you start doing this over and over again, and you realize that variations in etching and so will all of a sudden make your algorithm go all sideways and you're out of luck, it becomes a real problem. So that's why EBSD is so important to the serial sectioning process. Everybody on here, I assume, is fairly familiar with the technique, so I'm not going to go through that. But what I want to point out is that for us, the way that we're looking at this is not necessarily looking at the fine details of small changes in orientation, those types of things. Although they're important, they aren't the most critical thing that we're looking at. What we're looking at is the ability of EBSD to clearly delineate between features that we know are important, namely the differences between grain orientations, right? And so now we have an imaging method that is extremely easy to segment. I have a quantitative measure. I can say I want to have a misorientation gradient no more than this amount, say 3 degrees, right? And then that's going to label any kind of grain boundary within there. Any points that are within that threshold all become labeled as one single grain. And we know that that is directly tied to properties that we see as being important. So that's why EBSD is so critically important. And this increase with speed is something that's really also enabled this, right? When I first started doing this, I was somewhere in this domain of looking at, how quickly can we collect points? And we're kind of still in that area of like how many seconds per point versus points per second. And now with the advent of faster and faster cameras, the CMOS cameras that have recently come into the fashion, right, we are indexing over 1,000 points per second. So that is highly advantageous. Now, the next thing you may realize is that, well, okay, that's great, but you're still talking about having to take a sample and load it into an SEM and back out of an SEM, do all the polishing. And so that seems very labor intensive. And you're not wrong, but there's also solutions to that. And this is our solution. So this is the Robotic Serial Sectioning System for 3D. I have to first give credit to Mike Uchik and his development of the Leroy system at AFRL. He's the first one who kind of said, I think we could really join up an SEM and a polishing station by using one of these small industrial robots, and he's done that extremely well. What both of us have certainly found is that the most difficult part is scripting an SEM to work without a user. Here we're using a mirror test scan. It has a very open API, which allows you to basically control everything that you could do at a user interface through a Python API. And so building on top of that, a number of automated methods to make sure that we have accurate focusing, accurate positioning of our sample, all those types of things are quite critical. We do use fiducial marks to kind of help with the loading and unloading. Just the stage itself, we're finding that we usually have somewhere around an error of somewhere around 100 to 200 microns. On positioning, it really can depend a little bit upon how we design these pucks that we're attaching our samples to. But by using these fiducial marks, we get our accuracy down to about 10 microns of repeatability. I'm certain that with a little bit more work, we can probably get that further collapsed. I think we're 1 micron of accuracy is certainly within our grasp, but does require a little bit further redesign of how these pucks get fixed to the stage, and so we have that very accurately replaced each time. So what we're looking at here is a set of serial sections that we collected with the robot. It was 308 sections. We used a spacing of 1.5 microns. And we're using a 2-step polish. It's a 1 micron diamond finished off with a colloidal silica. This is all done on the RoboMet automatic polishing system. The EBSD data was collected as a 2x2 montage of tiles that using the montage was certainly advantageous because we didn't have to be as precise with things like tuning our dynamic focus for each section, which was going to be quite difficult to do, again, in this fully automated session. So we could have a little bit more play in that and still collect a fairly large area. For every every scan, we collected every one of the EBSD patterns. We saved those, and we did the post-processing with NLPAR, and I'll talk about what that is in a second. But that is basically, we saved everything as a 60 by 60 pixel pattern with a collection time of 1.5 microseconds. That translates to 660 points per second. Again, you can see the voltage there is 30 kilovolts with about a 10 nanoamp exposure rate. Just as a kind of give you an idea, it takes about 2.5 hours to do one section. 30 minutes of that is just removal and getting the sample clean and making sure that it's ready for a vacuum. And then the remaining time is all in the imaging. So there's a considerable amount of time that's spent imaging the sample. But I want to point out that, again, the choice of going with EBSD means that I'm not spending what would potentially be 10 times that much time segmenting the image afterwards. So even though it's a long time to collect this data, the net time savings are considerable. As you can see, though, keeping every one of the EBSD patterns is quite sizable. We end up with a data set that is about 10 terabytes, and we can do about 10 sections a day. So this is the sample that we're looking at. This was done by Oak Ridge National Lab. It's just a simple cube, and we wanted to see what was the bulk microstructure like. A couple of things I just want to point out. These were 30 micron layers done on a powder bed with a laser. And we have rotations between each layer of the raster directions of 67 degrees. This is done to reduce the formation of residual stresses, but it also is something that is expected to break up some of the crystallographic texture. And we'll see how well that works in a little bit. At the hatch distance of about 120 microns. So that's the sample that we're looking at. And so the processing pipeline for these sections, the data that we have, looks like this. And so you can see this is kind of a dense slide. I don't know if I'll go through all of it, but what I want to point out, I want to highlight some points here. Here's our 2x2 montage of EBSD maps up in the upper right-hand corner. We also collected backscattered electron images, and this was done at 0 degrees tilt, whereas the EBSD was done at 7 degrees tilt. The BSE images were relatively easy to align and stack. In that, we basically just had to look at translations and how do we translate over these relative to each other. This is done by looking at the phase correlation or cross correlation of the images. That gives us a relative translation from one tile to the next. And then we can use this data to actually segment out the pores that are present within here. In any kind of AM build, you typically have some small amount of porosity, and this is no different. So those pores are very obvious because they basically act like tiny little Faraday cups, and all the electrons go in, they don't come out, they look very, very dark compared to the rest of the microstructure. One of the things we did that we realized, though, is that the grain contrast was quite poor. And this is because of the amount of strain that is in the material, and so the variations in contrast within one nominally similar grain orientation vary quite a bit. And so it's very difficult to use the grain contrast as a comparison to the EBSD data. If you look and stare long enough as a human, your pattern recognition engine will recognize certain similarities, but it's very difficult to get that to line up with the EBSD maps. Now, on the side of the EBSD maps, what we did is we first stitched all these maps together. We have an algorithm that will stitch these together and give it a fairly seamless set of data. And then we did pairwise matching of all of the sections. So that's basically we matched section 0 to section 1. And then we are matching section 1, but not the new version of 1. It's still the old version of 1 to 2, old version of 2 to 3, et cetera, et cetera. That gives us how we need to move from each step to each step. We then can take that, we regularize that into certain displacement maps. So those displacement maps tell us exactly how each pixel needs to move. It was found that here we needed to use a fairly complex set of transforms in order to get things to line up. It's a combination of perspective transforms along with a second degree polynomial or quadratic function that gives us enough freedom of how do we warp these images in order to get them to line up, and then and get good matching from section to section. One of the things that we found out, though, is that because of the directional nature of the additive manufactured microstructure, you can get a large grain that kind of moves through your serial sections and can drag certain corners along with it. And so that required some further filtering of these displacement filters. And the thing that we did is we basically said, okay, eliminate any low frequency noises. We only want the high frequency displacements moving from section to section. That gave us a very good alignment of that data. We then segmented the pores out of that data, did a comparison between that and the BEC, found another set of transformations, aligned those two sets of data, and then we had a unified data set. And so we're actually using the segmented pore from the BSE images. It's a much higher resolution. It has a sharper image, and so we have a much higher resolution of those pores from the BSE, and then we're combining that with all the crystallographic data to form our complete data set. And you can see a reconstruction of it here. Just want to point out that as evidence that we probably did a fairly decent job of aligning all this data was that you have a hard time looking at this and deciding which one is the section plane and which one is the imaging plane, right? The EBSD maps seem to align and look fairly similar no matter what. You don't see a lot of stair steps or jags or anything like that. So that's a good evidence that we probably did a pretty decent job of doing the alignment. Now, the other thing I wanted to point out is that this collection of EBSD, I talked about how much time it took and how long that took. And this relates to some of the post-processing that we did in terms of the NLPAR. So the thing about EBSD data collections, I pointed out how much faster it's gotten, but if you compare it to other imaging methods, it's still not the fastest method out there. So if I'm looking at collecting a EBSD map, it's something around 3,000 points per second. If I'm looking at a 1 megapixel image, so something that even the oldest smartphone, right, could do, we're still looking at a 5-minute exposure time. That's one way to look at it, right? That's how long it takes to collect that. If you're looking at a 5 megapixel image, right, we're talking about 30 minutes. If I'm comparing that to the optical microscope, it doesn't really matter. Optical microscopes are a highly parallel data collection method, right? It doesn't really matter if I'm doing 1 megapixel or 5 megapixels. That can generally collect the data in about the same amount of time. But there are things that are happening in terms of looking at computation methods, and so that can really enhance how quickly we can collect this data. One of the first ones that came out a little while back was this NLPAR algorithm. This was pioneered by EDAX, and what they're doing is they're saying, like, look, your data is highly redundant. You have a lot of points in there that are extremely similar, and that it's very unlikely that your next point, or that you're surrounded by points that are very different. So what we're going to do is we're going to take something that has a very high or a very low signal to noise ratio, and we're going to combine it with its neighbors. And so we take all these 4 points, and we're simply going to take these and average those patterns together. And when we do that, we get something that's fairly easy to index. You know, all of a sudden you do see the patterns. That pattern was sitting there the whole time, right? And so you can actually have quite an enhanced way of indexing your data by doing this. This is a post-processing technique. If you save your patterns, you can do this. Now there's some things that come out of this. So if we look at, and that's because basically your signal to noise is increasing faster. The signal is increasing faster than your noise. And so there's a benefit to doing more and more patterns in terms of averaging, but there's some detractions to that too. And so if we look at this, one of the problems is that you can't use kernel sizes that are much larger than basically your nearest neighbors. The amount of mixing that happens between patterns that are at the grain boundaries become too great. You start losing the ability to index those patterns. And it's fundamentally biased against small features. You can see here that this twin here has disappeared in the NLPAR processed data. Start losing some things here, some of these smaller features that are present within the grain. And that's simply just because you're mixing in signals from somewhere else. So what we developed was a new version of NLPAR. We call it NLPAR. And NL stands for non-local pattern averaging and reindexing. And so here what we're saying is that we're not as concerned about the proximity, how close a pattern is to the pattern of interest in order to determine what kind of smoothing it should have or what kind of averaging it should have. But we're concerned about how similar is the data that's present within the two patterns. And so here we're taking that similarity of data as simply the Euclidean distance or between the two, the L2 norm of the patterns. And we're just going to treat each pattern as though it's just a vector of data. And the weighting factor is going to be basically an exponential decay of that distance. Now, there's a couple of other parameters that are needed. You need to have some estimate of the amount of noise that are present within the pattern, as well as this lambda value, and that's a user-chosen thing, usually on the order of about 1. That tells you how much smoothing would you like to do, how stringent do we need to be about how similar patterns are before we consider them to be averaged. And so that's what we're doing, and we can now do this over much larger window sizes because it'll automatically reject dissimilar patterns from the smoothing kernel. I have a couple examples of this. So here, I've extracted a point that's right along a grain boundary, and so the patterns over on this side of the map should be very similar. These over here will be very different, and so if I show you all those patterns, if you look closely, the patterns within the purple grain are quite a bit different than the patterns within the blue grain. And now what I'm going to do is I'm going to color this by the level of weighting. So the brighter the pattern, the more weighting it has within the averaging kernel. You can see that we're actually just lighting up patterns that are within the blue grain and not within the purple grain. And so, but that's not a very challenging scenario. Those patterns are very high quality. It looks very good. There's nothing very challenging there. But if we start adding some noise to our patterns, so here we've added a considerable amount of noise. And here's the set of patterns now with the noise added. This is a synthetic noise that I've added to these patterns as a demonstration. But you can see that we're still lighting up primarily patterns that are only in the blue grain, and we're ignoring the patterns within the purple grain. And it does quite a good job. And so now if we take those patterns and average those patterns according to those weights, this is what we get. The ground truth pattern is presented there. There's the NLPAR filtered version versus the original. So you can see that we have a very high quality pattern to index. Now, here's a much more challenging situation. This is taken from this sigma 3 boundary, a twin boundary within this nickel data set. Here are the patterns, and you notice that there's a lot of similarity between these patterns. It has a pseudo-symmetry type situation, right? Some of these poles are very much located in the same locations between the twin. There's some bands here that are very similar. So can this effectively differentiate between those two sets of patterns? Again, if we're just looking at these high-quality patterns, it's not much of a challenge. It certainly does a very good job. And in fact, you see that, again, we're highlighting only the patterns within the yellow grain. We're ignoring all the patterns within the blue grain. Now, if we, again, start adding some artificial noise, we'll see how well the algorithm performs. So again, this is all the patterns with noise added. And you can see it starts to become a lot harder to differentiate exactly which pattern should be there and what shouldn't. But when we run it through the algorithm, it does a very good job. And again, that you really see lighting up are contained within the yellow grain. And if we look at the reconstruction, you can see it does a very good job. It reconstructs exactly the pattern that we'd expect. Now, to just show how far you can go with this, I've added 350% noise. This is basically, we look at the standard deviation of the original pattern, added 350% of that standard deviation in terms of just Gaussian noise to this pattern. And so if you look at this, these are, if somebody said, okay, I want you to index those patterns, you would probably come back and say, they look like garbage. There's nothing there I can index. But if we run it through the NLPAR algorithm, what we see is that it still primarily is choosing patterns that are on the left-hand side in the yellow, within the yellow grain, and ignoring things that are within the blue grain. If we look at the reconstructed pattern, it's actually something you can index, and it actually does a fairly good job. And so that's kind of the power of this NLPAR algorithm, is that it does a very good job of making sure that it's filtering out patterns that are dissimilar from the pattern that you're interested in examining. And so it's very powerful. You can use windows that are up to, we typically will go up to about a search radius of 7, which translates into actually a 14 by 14 box of patterns. And so you can actually look at a very large set of patterns and use those to enhance the signal, and it does a very good job of differentiating and making sure you're preserving the features that you're interested in. So as an example, I just want to show just a little bit more here. This is a comparison between conventional indexing. Here's that noise ratio across the top. I apologize for the covering of the title there. But as we go up, we're adding further and further noise to these patterns. You can see that the conventional indexing basically falls off and you get nothing but noise. You can see the NLPAR does a fairly decent job, but the NLPAR, because we can use these larger search windows, is able to maintain a higher data quality for longer while still maintaining these small features. We haven't erased all these small features that you saw within the original data set. Some of you may be familiar with the dictionary indexing methods, and there's actually a lot of analogies between that and what NLPAR is doing. And here's a comparison between something that was indexed using dictionary. Hopefully it'll show up here. There we go. Using the dictionary method versus NLPAR, and you can see that they're actually very comparable in terms of their performance to extract meaningful data out of these low signal to noise situations. The thing with the dictionaries, you notice that most of the points are kind of more homogeneously distributed in terms of what it does not properly index, versus NLPAR concentrates much more towards the interfaces, as you might expect. Mark and I have been in discussions, and we're looking at basically how do we combine these two techniques in a really meaningful method. And so that's ongoing work, but we're very excited by that. We think that by combining actually both of these at once, we can actually have an even higher ability to extract meaningful data out of these very noisy patterns. So an example of the serial sectioning, bringing it back to what I was talking about before, the advantage that that gave us is that, as I mentioned, there's a high amount of strain within this material. And when you're using automated polishing, sometimes you don't get always the most ideal situation. We're using straight colloidal silica. It's not unusual, but we're not being able to do things like chemically etch and those types of things. And so being able to scan at a higher rate, we were basically able to capture data that was equivalent to scanning half the speed. And as I mentioned, our section time is highly dependent upon basically how quickly we can collect EBSD data. So this basically doubled our collection rate. By being able to use the NLPAR algorithm, we've doubled our collection rate. The original data was quite good, but you can see it's a little bit scruffy in some locations. And by being able to use NLPAR, we were able to actually get a very high quality of data out on every section and get a very good reconstruction from that standpoint. So this is the data reconstruction. You saw a reconstruction of this earlier. You can see that it has this elongated structure, as you might expect from AM. One of the things that was surprising, though, was exactly how large the grains were within this reconstruction. So here I've removed the outside box, and I've reconstructed the 40 largest grains within the structure. We thought for sure that within this volume, we'd have enough data collection that we wouldn't have a lot of grains hitting the outside edge. But what's surprising is that there's a large number of grains that are actually extending over 1 millimeter in length. We can see them span from one side of the reconstruction to the other. So again, this was a surprising result, but it was something that was very interesting. Now, the other thing that is remarkable is that there are still 30,000 grains within this volume. And so while these 40 grains are taking up the vast majority of the volume, most of the grains in the reconstruction are extremely small. They're very small. And there's also 1,800 pores that we identified. So it's just a very interesting microstructure from that standpoint, to have that breadth of grain size within the AM sample is something that was completely unexpected, as well as just the ability to have these very elongated grains. When I mentioned before, the raster direction between each plane is set up with the 67-degree rotation, this kind of prime number rotation, that should be breaking up any kind of crystallographic symmetry that you might expect passing from layer to layer. Now, if we do look at some of the EBSD data, right, if we just look at kind of some of the traditional things you can look at, you can extract grain. What does it look like? We see that if we color the grains by their IPF direction along the build direction, we see some trends. Namely, a lot of these large grains are green, and this is expected if you look at just the textures from typical AM processing. They typically will have this 110 texture along the build direction, and that's exactly what we see within our structures as well, is that there's a preference for the 110 along there. You can make out that there's probably somewhat of a single orientation texture within the 200 and then this fiber direction within the 111 that appears. And that's basically all of this preference of having the 100 along the build direction. And certainly there have been a number of papers that have shown that this is basically the overlapping of the weld beads and how these are the highest thermal gradients that do exist within each layer. What is striking is how this has the ability to pass from layer to layer, even though these weld bead directions are changing. The other thing we can look at is the porosity, and I want to show why that's important in terms of how we look at grain features. So there's a number of pores within here. You can see that some of them are very irregular. These are lack of fusion pores that are present. These are reconstruction of the 3 largest pores. If we were going to do this with X-ray tomography, we would have missed nearly all of these pores. This thin sheet here, it's extremely thin. It's only about 1 or 2 microns thick, but it actually extends somewhere around the neighborhood of 50 microns or 100 microns in the 2D plane. So these types of things are something that certainly are concerning and keep you awake at night if you're thinking about fatigue issues and those types of things within these AM microstructures. So if we look at a reconstruction of these, we can kind of segment them out. The other thing is that there's a vast number of these gas entrapment pores, very small little pockets of gas that got trapped, and we can tell that they're very different because they have this high spherical ratio here. And we can measure that sphericity ratio by looking at the ratio of a diameter of the inscribed sphere versus a caliper diameter. Anything that's close to a sphere should be 1. Anything that's very irregular is going to have a lower value. And you can see that if we just take kind of this trough in that plot and split it into 2, we can kind of split this into these irregular pores versus the small spherical ones. And why I say they're small is that if we look at this histogram of the pores within the structure, this is the caliper diameter for those pores. The blue bars represent the things that are labeled as spherical pores. You can see they're all fairly small, biggest ones topping out at no more than about 15 microns in diameter, versus these irregular pores stretch out, and some of these reach out to over 200 microns in a caliper diameter. Just want to point out just how skewed this distribution is. This is actually a log scale across the bottom. So we have this very large dispersity in shape and size of these pores. Now, the other thing is you can see that they kind of line up with certain layers, and we were wondering if that has any kind of correlation with the grains that we see within the microstructure. So what we did is we said, okay, we want to label every time a new grain arrives within the build direction. So this is basically, it's akin to a nucleation. I hesitate to say that it is the nucleation location because of the number of overlapping weld beads that happen within AM, but it is the first time that a grain shows up within the structure. And so we gave it each one of those points a little dot. And then one of the things we immediately noticed is that some of these dots are very much clustered, while some are very spread out. And so we labeled the clustered dots with a red point, and then we look at the unclustered ones with a blue point. And one of the things that we notice is that we do see, where we see clustering of pores, we do see similar clusters of grains, but for the most part, they aren't a one-to-one correlation. We can see a cluster up here of new grains showing up, but the pore that's associated with that is actually inside the cluster. It is not below the cluster. The cluster starts lower than that grain. Same thing with this cluster down here, even though the perspective makes it look like it's next to this pore, it is not. It's actually deeper within the sample. And so this cluster down here is again, kind of off by itself. Contrast that with one of these lack of fusion pores, and specifically this one up here. You can see there's a whole bunch of red dots that sit right along that edge. And that's actually a nucleation of a bunch of new grain orientations that show up with this particular cluster. I point out those 3 because those 3 are the 3 largest clusters that we see within the reconstruction, and I've reconstructed them here along with all the grains that come off of them. So here are I think this is the 5 largest or the 10 largest set of clusters. This one here, this is that grain that I showed that has all those grains starting off at the top of the pores and branching out, you can see how short-lived they are. They do not last long. In fact, if we look at how long does a grain last, how many different AM layers, the vast majority are gone within one layer. 50% of the grains only exist for one layer, and only 13% of the grains exist past 3 layers. So basically, the vast majority of the grains do not make it past the 3rd layer. But out here at the end, there's these exceptions, and here's a great example of this. And quite surprisingly or serendipitously, it's labeled gold, right? This is just the IPF color of its direction along the build direction, the IPF direction along the build direction. And it's kind of the Goldilocks grain. It is the grain that is not ideally oriented for any one layer, but it's well oriented for nearly every layer. And so we see it passing from layer to layer and growing and getting larger and larger. And you can see it, we don't actually capture the whole grain. It continues to grow past our analysis volume. But then I contrast this with this grain here. And this has a very different morphology associated with it. You can see that if we looked at that cluster of new orientations, it's very akin to basically a new powder particle that came into the melt, partially melted, and then started solidifying off of that partially melted powder particle. And so we see that as being another major instance of how do we have new grains showing up within these AM builds. And that would be similar to the formation of this cluster. This is the cluster I have reconstructed, this cluster here, and also this cluster here. Again, the perspective here is a little bit deceiving. It seems like it's associated with these pores, but those are actually closer to you in the reconstruction. This is a little bit deeper back. So that cluster is actually independent of these pores. So we found that to be a very interesting result, and it was kind of a fun thing to see how these grains cluster and the pores cluster, but we think that most likely this is due to some poor alignments of the AM structure, or some poor raking of the powder during that part. And we're not sure if that's associated with the gas flow or if that's associated with the lineup of the raster direction with the other features, but that's what we saw. Last thing I want to point out is this idea of looking at local arm orientation. So it's clear that we have these arms that are streaking out within these large grains. And one of the things we can do is we can reduce these shapes down to a set of representative ellipsoids. And these representative ellipsoids basically align themselves along with whatever the morphology direction is within that local shape. And so I won't go through all the image processing that we did to do that, but the idea here is that we can measure the crystallographic direction of those ellipsoids and ask which direction are those arms pointing. And so when we do that for this particular grain, this is the result we get. So I'm just plotting this as essentially an inverse pole plot. And you can see that the vast majority of these grains all line up along 0, 0, 1. These are the fast growth directions within additive manufacturing. It's not surprising, but it is kind of surprising to what degree it's dominating the morphology of these grains as they grow from layer to layer. If we look at the entire structure, we analyze all of the arms within the entire AM structure, we again get this high degree of alignment of 0, 0, 1 directions. So all of those branches and arms and zigs and zags you're seeing, those are all along 0, 0, 1 directions. And it really talks about how dominant that fast growth direction ends up being for the growth of these morphologies within the structure. I think I have one more set of slides, but I think I'm going to skip that for now. And I'm going to see if there's any questions that we can get to right now and make sure that we have time for that. And if I have time to talk about grain boundary crystallographic preferences, I can. But I think at this point, I'm going to put myself on pause and see if there's any questions out there. So I am seeing a few. I'm going to start here at the beginning. First question. Can the polishing with fiducial marks really be called simple, as you need to renew the fiducial marks for every few slices or so? That's a very valid point. So in the case of our 3D reconstruction here, we were putting in fiducial marks and we would have to replace those approximately every 10 times. That was very advantageous from the standpoint of that's about how many we could do in one day. So that meant that every day we'd have to have somebody come in, pull the sample off, and do the indents. We didn't have an automated indenter that would do that for us, but it certainly is not something that you could certainly conceive that something could be constructed to do that. But the other thing is that a lot of times we can use the microstructure for alignment. And so the fiducial marks are a handy thing for looking at depth removal, but they aren't as critical for looking at microstructural alignment. And so that's just kind of one of those things. So in fact, when we would run over the weekend, we would actually let our indents go away. It would be removed from our sections, and we'd have to come back and basically place them back in. So we got by without having hard fiducials on every one of our sections, but they were handy to have there for both depth removal, just make sure that we were on track with that, as well as some of the global alignments. It was handy to have that as a marker. Let's see here. How's the automatic control of the 3D EBSD system arranged? Is it through custom-made software, and if so, in what language? And so they are also they're wondering about how do we interface with the EDAX team software. So yeah, the vast majority of that is done with a Python scripting with the TestScan Mira, as well as talking to our robot and sending some signals to the RoboMet. So that's mostly done through Python. And then we're negotiating through the Teams API. And yes, we are continuing to work with EDAX on that and to make sure that it's robust. I think one of the things that we have is that's unique is that we are running this for days and days on end, which is admittedly a very difficult set of troubleshooting to do if you do have problems. But we found it to be reasonably stable. One of the things that when we were designing this whole thing, though, was we had a philosophy of if the system ever feels confused, please come get a human. And so that's very much built into how everything works. We actually have something that will notify us on our mobile phones that if the machine gets confused, please come check on me. We can often just dial in remotely and maybe solve the problem. Sometimes we have to be there in person, but that is kind of the thing. And there are a lot of checks to make sure that everything is working properly. We do independent checks to make sure that the EBSD camera is inserted properly and retracted properly. We do that through the IR camera on the Mira, as well as having checks with the EDAX software. So there's a lot of that type of thing that's happening in terms of making sure that the system works smoothly. And that's not just the EDAX side of things. We see that we are doing those kind of checks across all the different systems. Have we ever encountered unmolten powder particles that are partially or still martensitic? We have not seen any evidence of martensite in any of the reconstructions. We did use both the ferrite as well as an austenite phase for looking at the EBSD reconstruction. We also did some X-ray diffraction on the sample beforehand, and we saw no evidence of any BCC within there. Of all of the things that we saw that do look like unmelted powder particles, they still very much look like they are all austenitic. So even with these very rapid cooling rates, everything that we're seeing is austenitic. That is backed by some work that we've done with Tony Rowlett, where he's looked at some synchrotron experiments and looking at the solidification path for 316. And it's dependent upon how quickly you're printing, but at these very high cooling rates, they were seeing only an austenite microstructure. And I think that actually applies as well to the powder. And it may very well be too that the powder is getting hot enough from subsequent passes that it also is maybe translating. So the question is how can we index or measure accurately acicular ferrite, carbide-free bainite, and lath martensite? As these all belong to the crystal structure of BCC and BCT. So if we were looking at, I'll just give a little bit of insight, certainly not necessarily in the scope of this particular talk, but I would say that one of the things, if you look at Mark DeGraff's work with looking at dictionary indexing, there are some chances for doing a fairly good job of capturing the very small strains that are associated with that BCT microstructure that the traditional indexing does not capture. It's very difficult for the traditional indexing to pull out those small changes in the lattice parameter. And I would say that's probably your best bet for most of that. In terms of the difference between lath martensite, bainite, and acicular ferrite, those are things that we've been investigating at NRL through the years. We find it tends to be very alloy dependent, and there are some things that we've discovered for looking at very low carbon alloys that make some sense in terms of looking at pattern quality and those types of things. But I will admit it's still a very heuristic decision in terms of how do we do that. And it's not really a quantitative thing. I think there's maybe some other techniques we need to look at. And the world of all those bainites and martensites are extremely complicated. And I think it's one of the great challenges of like, how do we as metallurgists clearly identify between those phases as in terms of looking at a definitive processing route in terms of its formation. So yeah, you're wondering, the next question is looking at the Hall-Petch relationship and how it can be applied to additive alloys. Yeah, and I think that's one of the things that our work that really brings out is how do we properly look at something like a Hall-Petch relationship? My suggestion would be is that we have to have a different size metric. You know, the Hall-Petch relationship is really based upon thinking about space filling, nice equiax grains. And here what we're looking at is basically, we could do a very easy measurement of average distance to an interface. It require, kind of reformulating things a little bit, but that's a metric that's actually not that hard for us to calculate. We can take every voxel within the structure and say, what is its minimum distance to an interface? And so I think that that might be really advantageous. Some of it is kind of going back. I've seen some people looking at back calculating what would be the equivalent Hall-Petch size, and does that match any of the microstructural elements we see? One thing I didn't talk about was some of the segregation that it forms during this. There's the cellular structures that form on the sub-micron level, and some of the work has shown that that's actually the length scale that's most appropriate. You did see a lot of sub-grains that were within the EBSD maps. And again, that's maybe the most appropriate grain size that comes out in terms of describing some of these, the grain size of the structure in terms of a Hall-Petch relationship. Are you sure that these large areas are grains? That's a very good question. My recent TM studies, I think this is getting to what I just talked about. They might be several separate grains that grow almost epitaxially on top of each other. And I think that's exactly the point, is that if you look at the detailed formation, there are these cellular structures. We think this is happening basically from like a cellular solidification standpoint, that you do get some level of segregation that forms in between what would be, dendrites, but they don't really have time to develop arms of the same orientation. And they are growing epitaxially. We think they very much are growing epitaxially from layer to layer. And what's interesting, and I think what this slide that I have up is showing, is that even though that's happening, like I say, on the sub-micron scale, that is something that we're seeing reflected in the more mesoscale microstructure as well. So those clusters of cells are actually still adding up to a fairly textured, morphologically textured sample. So I think there's still a lot of work to be done in terms of figuring out exactly that relationship, but I think that your results and what I'm seeing are very consistent with each other. Yeah, so somebody said, can you talk about the grain boundary interface texture? That is called seeding your audience with good questions. So, so if we're going to look at grain boundary character distribution, this is made up of a 5-parameter space, right? So we have 3 parameters that describe the misorientation, 2 that describe the interface orientation. You usually need a large number of grain boundaries. Luckily, we have them. So the way that this is going to be represented is we're going to extract individual misorientations and look at what types of interfaces are present for a given misorientation. So that's my very fast blow by of what a grain boundary character distribution looks like. And here's what we have. I'm going to compare this to some data that we have on traditional 316. So this is additively manufactured on the top, traditional equiaxed, highly twinned 316 on the bottom. You can see that the traditional material has a very high prevalence of 111 interfaces like you'd expect. And then the additive manufacturing is the opposite. If we look at low angle boundaries, so these are only 5 degrees of misorientation about the 100. Again, we see a prevalence of 111 interfaces in the traditional material, a depletion in the additively manufactured, but a preference for 001 orientations. I'll note that this is different than preference for the 001 morphological directions that we saw previously. If we look at something like a sigma 5, so here this is a tilt boundary, formation of a tilt boundary in the additive manufacturing sample with a combination of twists. And then there's kind of the opposite relationship again in the traditional material. And one of the things I'll point out is that this is the set of boundaries that gives you the most 001 interfaces. These set of twists and also this set of tilts. And if we look at the sigma 3, we have something that looks dramatically different than what we'd expect from traditional 316. You'd expect 316, you'd have this huge peak that's associated with the sigma 3 coherent twin. And that's exactly what we see in the traditional material. I want to point out the multiple random here is almost 6,000. And here's what we see in the additively manufactured material. There's almost no coherent sigma 3s within this material. In fact, just the number of sigma 3s is quite low, but there are almost no coherent sigma 3s. And what's interesting is that we have this ring of interfaces that surround the sigma 3. They exactly lay on top of, and this is the only way that you can get this within this type of boundary, the 001 interfaces. The rest of these peaks are simply symmetric reflections of that one. So again, we have this preference for 001 interfaces. And so we find this to be very intriguing. There's a lot of things that we don't fully understand about this, but we're moving forward. We think it makes sense from a certification standpoint that you wouldn't form those coherent sigma 3s. What we don't fully understand at this point is why do we always have this preference for 001? It doesn't necessarily make sense with what we'd expect, but yeah. So, all right. There's a question from how does NLPAR impact other measurements like CAM or GOS? Those are things we have not researched extensively yet. Everything that I've looked at least qualitatively, shows that you have a sharpening of the information. Let's see if I can scroll back here to my example of my 2 AM data sets. Not that one. So I'm not sure if you can zoom in enough on these images, and I can certainly, I think the PDF is included or will be included with this. But if you take a look, you can see a lot of these subgrain formations within these grains, these slight changes in color in the IPF maps. And what we see happening within the NL process things is that where some of those boundaries are a little bit fuzzy before, they actually become a lot sharper. One of the things we'd really like to do is start running some simulations using things like dictionaries to make sure that that sharpening is real. We tend to think that it is because that is more similar to what we see within TEM investigations and those types of things. And so we think it's actually a fairly accurate representation. Like I said, there's a lot of analogies between the dictionary indexing methods that Mark DeGrasse has developed and NLPAR. And specifically, the metric that we're using for measuring similarity is essentially the same. The difference is that I'm not looking at a whole dictionary of orientations. I'm only looking at a narrow neighborhood of orientations to compare to. So from that standpoint, we think that it's probably very likely that these sharp interfaces are real. And so it might actually be enhancing our ability to interpret things like CAM and GOS. Like I say, I think that would be a very interesting thing of research for somebody to pursue. So I'll just leave it at that. But right now, qualitatively, it looks very encouraging. Next question is, can you please, what program am I using to convert the data from 2D to 3D? How am I doing all this reconstruction? What program am I using for using the 3D data? So this is maybe going to be a very unsatisfying answer. I use a scripting language called IDL, Interactive Data Language. It was one that when I first started learning it in grad school, it was very good at handling 3D data. Python was still a complete mess at that point, and MATLAB was not handling 3D data nearly as well. So that's what I've developed almost all these scripts in, is interactive data language, IDL. If I am suggesting to somebody today, what would I use? I would use Python with a combination of NumPy and SciPy and those types of things. It's come a long ways. In fact, I'm translating a lot of my codes over, but still all of this reconstruction data is done within IDL. But really, it's a replication of a lot of the EBSD routines. These IPF maps are made using that software, using the standard, triangle for coloring, those types of things. They're just re-implemented inside of IDL. So yeah, that's what this language is. So. I consider broad ion beam milling and looking to automate that. Yeah, that is certainly something that I considered, and I've looked with great interest into the broad ion beam methods. I think Philip Withers has done quite a bit of that over in the UK. Has started kind of pioneering that method. And when we were trying to make our purchasing decisions, it was making the decision of, do I want to try to invest in something that's very much in kind of an alpha stage. The broad ion beam milling was just coming online, and did I have time to invest into trying to figure out how to machine, all the automation for that, or do I go with what I know and that we've been doing kind of successfully for a long time, and that I thought would be highly adaptable to a lot of different situations. And so that's why we went with the mechanical polishing. That said, I'm very encouraged by the broad ion milling, and I look forward to seeing some of those results come along as well. So, all right. So let's see here. Somebody is saying that they are looking at AM alloy, but there's some black area. We're not able to identify it. I have no idea. I can't help you with that. I'm sorry. Certainly we see black areas from pores and those types of things. It may be that you're having some kind of phase transformation, might be ferrite that's occurring. If you're looking at let's see here. Oh, this is maybe a aluminum alloy. Yeah, I'm not sure. I would not have any insight on that, but so, and all right. Very good. Peter Kronenberg has a question of how am I remapping the orientation data, and how am I dealing with interpolations and those types of things. So very good question, Peter. So there's two things. The first part of the answer is the disappointing one. I'm using nearest neighbor resampling. So that's how I avoid having to figure out how to interpolate. I don't. I just grab the nearest index point. But what I want to say is that the way that we had set up this original pipeline of all of these different transformations and everything like that is that we are saving, we're saving not the transformed images, but the list of transformations. And so it ends up being this very long list of exactly what transformations go into making up your data. And so the final reconstruction is actually going back through that whole chain of transformations and referencing the original data just one time. So we're only doing one resampling. And so that really greatly eases things. Now, that would get back into then how would I consider something like looking at CAM or GAUSS. We'd have to be careful whether or not we're replicating data points and how those get put into the reconstruction. And I haven't gone through and done an analysis yet to see if that, how much that's occurring. But that's the way we're dealing with the resampling at this point. I hope that answers the question sufficiently, but we're kind of trying to do the best of both worlds. So, yeah, I think that's all the questions that are listed. And if there are any others, I'm happy to take them. Otherwise, I really appreciate the time that you spent and listening to me talk on for over an hour. So really do appreciate it. Thank you.